Okay, I'm going to record this for all the juniors that are not here. Right? We're going to do a lot of material today. We're going to try to catch up. Now, a word on the digital learning days. If you sent me something, I think almost everybody did for both days. If you sent me something or you contacted me, I got credit for attendance. You sent me the digital learning day bond guard problems, right? I've got those. I don't have the grade recorded yet. It will be recorded. And if you sent me your exponential stuff from yesterday, I've got those. And I'll grade those, and you'll get a grade recorded for that. If you did not send me something, you can submit it late with a letter grade deduction. So if you didn't get me yesterday, do it today, send it to me, right, and I'll record it as a letter grade. Dr. Mayani's pretty adamant that everybody is going to get 2 grades for the 2 digital learning days. Okay. So we're going to do that. This is the one of the problems I did on the video. Problem. Yes. What are you doing with the hard copy? Didn't I ask you to turn this in on Friday or Thursday? Okay, so this is one of the ones I did on the video. This is an exponential growth problem. If you looked at that, how many people saw the little video? Okay, did it make it easy? Yeah, we're going to do this one very quickly. This says that the weight, right, the weight of the puppy is increasing at a rate to its weight. So the rate of change of the weight, we'll use time for the independent variable, is directly proportional. There's a constant of proportion to its weight. Okay, so whenever you see that scenario, that's the exponential growth. The other thing you should probably realize is that this is because in biology, nothing grows this way. Right? If you think about, well, think of human growth just for a minute. If this is time and this is weight, a baby's fastest rate of growth is at birth, right? So they take on, time is 0, whatever the initial birth weight is, grows very, very rapidly. Okay, then it starts to slow down, and then it pretty much levels off or a very, very slow increase until you hit, I don't know, 13, 12, wherever your puberty is, and then all of a sudden it goes up again. Right, and then when you become an adult, it levels off again, unless you're really, really old, and then it starts to go down. Right, old people shrink, right, because vertebrae get compressed. Right? So if I was 6'1" now, by the time I'm 80, I won't be 6'1", I'll be shorter. Yeah, the cartilage in the vertebrae starts to get collapsed, and so you get shorter and shorter. Yeah. Well, I don't know. If you're full size now, yes, when you die, you will be shorter. The good news is we don't have to get as long in a coffin. So we can get shorter. There you go. This particular puppy problem has the weight proportional. The rate of growth of the weight is proportional to the weight, which is exponential. It does this, right? And that's crazy. And nothing. Clifford grows this way, right? He just gets bigger and bigger and bigger and bigger. But it does say, you know, during the first 6 months, so maybe there's some sort of, it's growing exponential and then maybe it levels off. But the task was to write down the equation and then put in 3 for t, right? And I gave you the shortcut. See how many people remember how to do this. What's the first factor? I'm telling to you, Leah. I have no clue. What's the first factor? What's the first factor? What's the first factor? What are the equal sign? 2. After that, there's an exponential expression. What's the base? What's the base? 3.5 divided by 2. What's the exponential? Or the exponent? T over 2. You had 10 problems like that yesterday. They take just that long. It takes 10 seconds to do. You do 10 of them, hit send, and you're done. You get an A+. If you didn't watch the video, probably you should do that, right? These exponential growth and decay questions go very, very, very quickly. Now, when you write down the equation, the first thing you should do is check to make sure that these two data points, there's two data points given in the problem, make sure that they are satisfied by the equation. So a puppy weighs 2 pounds at birth. Say, oh, 2-pound puppy, is so cute. And 3.5 pounds 2 months later. So the weight of the puppy at 2 months is 3.5, right? So those are the two data points. If we draw a little graph, and this is time, and this is 2 months, and these are pounds, weight in pounds. So here we are. Our first data point is right there. That's this one. W of 0 is 2, right? So this is W going up, and time is going off to the right. Right? And then W of 2 is 3.5. So this is 2 here. Here's 3.5. 3.5, and W of 2 is 3.5. Right, and we have this exponential growth going on. The way the puppy is taken off. I guess down here these would be negative time. So like in utero, the fetus is growing. Right. Yes. Okay. And the question that we're trying to figure out, how much does a puppy weigh at 3 months old? So somewhere over here at 3 months, there's a number up here. That's what we have to come up with. You know, how much does the puppy weigh at 3? It's growing exponentially, and we have these two data points. Okay, we have the equation. You just write the equation down very quickly. You got that. And then the first thing you should probably do is make sure that the equation makes sense. Yes, it is exponential, so that's this. This is the exponential part. And we have the two data points. If we put 0 in for t, we get, let's see, we get 2 times 3.5 over 2 to the 0 over 2 power, right? But 0 over 2 is 0, and 3.5 divided by 2 to the 0 power is 1, so we get 2 times 1. Okay? So sure enough, W of 0 is 2. Now, I probably shouldn't say this, but I'll mention it in passing. Please, please, please don't go canceling the 2's. That's illegal. You can't do that, right? Please excuse my dear Antella. You have to do the exponents before you do the multiplication. So no, don't go doing that. Do the exponent first. Okay? So in this case, we put t was 0 in there, and we got 0 here. We did the exponent, 3.5 divided by 2 to the 0 power is 1. Then we do the multiplication. Okay, so the first data point works. Let's look at the second data point. The second data point was W of 2 was supposed to be 3.5. So let's see if that fits in there. We're going to put 2 in here. So W of 2, which is 2 times 3.5 over 2 to the 2 over 2, right? We're putting 2 in for t. So 2 over 2 is just 1. And so let's go ahead and take care of the exponent. 3.5 divided by 2 to the first power is 3.5 divided by 2, right? Okay, so then once you've done the exponent, you can go ahead and cancel, and you get 3.5. Okay, so the two data points fit, and we do have a differential equation. Now, the other thing you might want to do, let me write this thing a little bit more cleanly. By the way, I gave you a bunch of these, right? You were supposed to just write down the equation. Put the initial value here, put the second y value divided by the initial value, figure out what the exponent is, check, make sure the points work, send it in. W is equal to, W was equal to 2 times 3.5 divided by 2 to the t over 2 power. Okay. The question was, how much does the puppy weigh when 3 months old? It's got to be one of these side answers for your Digital Learning Day, I didn't give you any multiple choice. You just had to write down the answer. Okay, how much does it puck? Did you like the cockroach problem? Did you go, oh? Did you go, yeah, ugh. Okay. And I gave you a puppy problem, and then I gave you a cockroach problem, and I gave you, I don't know what else. They were in there. Water bugs are cockroaches, believe it or not. Same things. Yeah. The only reason called water bugs is people go, yeah, I got water bugs at my house. I look at the water. If they said, I have cockroaches at my house, you go, ugh. Let's answer the question. Now, let me make a sort of a weird statement here. If I said, I'm trying to answer this question, how much does the puppy weigh when it's 3 months old? And I wrote W is equal to 2 times 3.5 to the 3 over 2 power. That's wrong. Okay, that is not correct. Now, but that's how much it weighs, Mr. Buffy. Absolutely correct. I agree. That is how much it weighs, but you can't write that. So let's see what's going on. W, we know, is this exponential growth function. This is W. Right? Here's time. Here's W. It looks like that. Puppy's growing. Red. Clifford. This W is not exponential. This W is constant. Right? It just goes like that. That's a number. So which one do you want? Do you want the growth or do you want the constant function? Well, W is in fact exponential. W is not constant. So you can't write W as that and W as that. Those are two different things. W is supposed to be W. So what can you do? Well, the first one I'm not going to recommend, but I'll show it to you because it's correct. If you said W is equal to this number when T is equal to 3, and you had that all as one line, I would bet that's correct. Okay, you do that. Here's a better option. W of 3, right, is equal to that. So this would be better, and I'm going to recommend that when you answer the specific question, you do that. Now, there's a couple of interesting things going on here that you need to be aware of. The first time students think about it, they get confused, but it's important to understand the notation. And the blue and the black here sort of show the two things I want to talk about. In this scenario, where I've got W is this increasing exponential function, the variables are named T for time and W for weight. Right? So in this case, W is the dependent variable. Weight depends on time. So think X and Y. This W weight varies with time. So W is a function of time. The weight is a function of time. Right? Weight depends on time. So I'm using function notation here. Now, there's nothing magic about using the letter F. My independent variable, I'm going to keep that T for time. I'm going to leave that there. But this could be G. Maybe W is growth of time. So now I'm going to call the function G. I can call it F, I can call it G, I can call it whatever I want. Probably the most useful letter to use is not F, nor G, but W. So in this equation, the W is the name of the variable, but it's also the name of the function. So when I wrote this, hang on. Make the teacher look dumb. Okay, when I wrote that line, the W here was the variable. Right? It was the variable. It was the weight. The weight was that number when time was 3. When I'm writing it like this, now W is the name of the function. And the name of the function happens to be the same as the variable, right? W is W of t. And certainly this is a lot more concise, right? Because you don't have to put that extra garbage on the back. I am going to tell you that if you write this, you won't get credit for it. That's not what W is. W is this. W of 3 is this. So yeah, you could do this, and this is what I'm going to recommend. That's the answer. Okay. Now, at that stage, you had to just jump on your calculator and figure out what the number was. I think this one worked out to be 4.6, wasn't it? Yeah. Okay. Now, the shortcut was very easy. You put the first y value, you put the second y value, divide by the first y value, and then figure out what the exponent was. Make sure your 2 data points fit. Just as another real quick example, let me just make up a new problem. This is similar to what you did yesterday. Hopefully you did it. If you didn't do it, you can do it now. dy dt is ky. Y of 3 is 2. Y of 10 is 8. Okay? This tells me growth or decay. Let's see, am I getting bigger or smaller here? Is this growth or decay? This is growth, isn't it? Right? So 3, 2, there's that, and then 10, 8. Yeah? So this is growth, yes? Okay, exponential growth. But it also works for decay. So the equation, y equals, what do I write first? 2. Then what do I write? 8 over 2. Can I simplify that to 4, Mr. Prescott? 8 by 2 is 4, but I'm going to leave it as 8 over 2. Now, exponent, and we're going to have t's in here. It's got to be, this is where it takes a little bit of thinking. If I put 3 in, right, if I put 3 in for t, this whole piece right here has to go away because I'm supposed to end up with just the 2. Right? All that has to go away. So what do I want? T minus 3? Yeah? Okay. T minus 3. You put 3 into this. Doesn't this become 0? Right? And 4 to the 0 is 1. 2 times 1 is 2. Okay, so that gives me that one. But I also need the second data point. So divided by what? How much? 7. Okay, so let's double check and make sure that works. If you put t is equal to 10 in here, right? 10 minus 3 is 7. 7 divided by 7 is 1. 8 divided by 2 to the 1 is 8 divided by 2. And 2 times 8 divided by 2 is 8. Right? So you can get the equation very, very quickly. What I would like to do today, however, is not to use a shortcut. I did this once on the video. You should probably go back and look at it again and compare it with your notes for today. Because most of the problems that you're going to encounter will not have the shortcut. These 4 that I found, and this is one of 4 that I gave you, were ones that were on the AP test. It is typically a quick problem, a short problem. You just write the answer down. You should be able to get the answer within a minute or 2. You got your calculator, you can get the answer. Most of the free response problems, however, are much more involved. They're much longer, and they take 10 or 15 minutes, not 1 or 2. So let's do this sort of the long way. I got dw dt is kw. And I know that w of 0 was 2, w of 2 was 3.5. And I want to figure out what w is. Now, given the exponential nature of it, I could just write the answer down. However, if this was kw squared, no longer is that exponential. I can't just write the answer down. I have to do this a different way. Okay? And the way you're going to do these is to separate the variables, separate and integrate. Let's do it with kw and make sure we end up with the same answer. Okay, so the first step in this process is called separating the variables. For the free response questions, almost half credit is just for doing this step. Separate the variables. If you don't separate it, you lose half credit right off the bat, and you get nothing much after that. So what do we mean by separate? Well, the variables here are w, that's the weight. I know that's also the name of the function, but it's one of the variables. And the other variable is t, right? Time. K was an unknown. It was not a variable. It was a constant. It was the constant of proportion. Okay, so to separate the variables, what you do is you take all the w's and move them to the left, dw over w, right? I'm dividing by w. And then all the t's you put on the right, so that's k dt. That's the separate stage. All the w's are on one side, right? Divided both sides by w, multiplied both sides by dt. Okay, so that's pretty easy. Now, occasionally you'll get equations that cannot be separated. For example, if I said dy dt is 3y plus 2, 3y plus 2, you can separate this. I want to get all the y's on one side. Any idea? I got to get this 3y over there. Okay, so if you subtract 3y, that would give you dy dt minus 3y is equal to 2, right? But then I got to get all the t's on that side. Well, if I multiply by dt, I got to multiply this whole thing by dt, then I get dy minus 3y dt is 2 dt. Well, I don't have all the t's on one side yet. Okay, so the only way, and we're going to see these not today, we'll see these probably tomorrow or Tuesday when we get back. The only way to separate this one would be to not subtract, but actually divide. Divide both sides by 3y plus 2. And multiply both sides by dt. Right? If you do that, then these dt's cancel, and you would get dy over 3y plus 2, and on the right side you would get 1 dt. Right? So all the y's are on one side, all the t's are on the other side. That's the only way to do that. There are equations, however, that you cannot separate. And again, we won't see these today. If we had something like dy dt was y plus t, that's one that you cannot separate. So there's no way to solve this differential equation in this course. There are methods that you can use, but not in this. What do you do when you encounter something like that? You guys are going to have to do it approximately. There are two approaches we're going to use. One is called sloped fields, looking at pictures of slopes. And the other one is called Euler's method, doing little tangent lines. That's not today. This is the one we're messing with today. Okay, so separate, we've done. The second step is to integrate both sides. Okay, so we're just going to integrate both sides of this equation. Now, integrate does not mean throw a squiggle here. Throwing a squiggle in there means throwing a squiggle in there. That's not, it's indicating that we're supposed to integrate, but you have to integrate. So this one here on the right side is pretty easy. Remember, t is the variable, k is a constant, so I can bring that out. So I have the integral of 1 dt, which is going to be what? The integral of dx is x, the integral of dt is t. Okay, so this just becomes kt plus a constant. How about the left side? This is going to be a natural log. It might be easier to see if you wrote it this way, 1 over w dw, right? So 1 over w dw, you know our integration rules. The integral of 1 over x dx, right? Is natural log absolute value of x, right? Okay. The integral of 1 over w dw is the natural log of the absolute value of w. Okay, so now we have integrated both sides. We got credit for separating, and we got credit for integrating. A little note here about my constant. Technically, there's a constant on both sides because, you know, I was jumping down your throat. Here's a constant C1, KT. Here's a constant C2. But if we subtract C1 from both sides, we could write it this way, minus C1. But C2 minus C1 is just another constant. Let me just call that C. So typically what you do is you put the constant on one side, the side that does not have the variable you're looking for. You're looking for W. Okay, so we've done the integration. And by the way, if I'll show you some free response questions, but if you see the rubric, if you forget the C, you probably lose 2 out of 9 points. You lose about 25%. But we're just not putting in a C. Okay, now, next note is, how about this absolute value of W? Okay, so you need to analyze this. You need to analyze, what do we mean by the absolute value of W? W represents the puppy's weight. Weight is always positive. So the absolute value of W is the same as W. Okay, so we just get rid of the absolute value sign, right? And the note that you should, have here, whenever you throw this absolute value in, it's going to go one of two ways. It's going to be the same as W if W is bigger than 0, and it's going to be the opposite of W if W is less than 0. Right? Obviously, weight can never be negative, but there could be dependent variables that are negative, and we will see some of those tomorrow. Okay, so analyze this absolute value garbage and take care of that. If W happen to be negative, then just replace the W with minus W. How do you know whether W is positive or negative? You look at the data points. So this is from the data. Now, if it's weight, something like that, I suppose you could say, yeah, I know weight is positive all the time. But if it were temperature, if we're doing the rate of change of temperature, temperature can be positive or negative. And so you're going to have to look at the data to see whether or not it's the positive side or the negative side. Okay. Next thing we need to do is solve for W. This is step 3. Okay, so if you remember your algebra, W is e to the kt plus c. Now, I've taught this class enough to know what's going on in your little heads out there. Some people are saying, got it, keep going. Other people are going, hold the boat, what happened? So let me just remind you, pull up a new screen here just for a minute. In Algebra 2, or in pre-calculus, you had this idea of logarithmic expressions. Log base 10 of 100 is 2, 10 squared is 100. Right, remember that? So this allows you to change log expressions to exponential expressions. And in our problem, if we go back and we look at the log expression, that's this right here, the natural log of W. So let me put that here, log base E of W. That's the log expression, log base E. On the right side of that, we had this, KT plus C. So that would fit right here, KT plus C. So I'm just sort of doing the analogy with the Rosetta Stone. Yes, I glued it back together. So I rewrite it. E to the KT plus C is equal to W. Right? And that's where I got this expression, this expression right. Okay? Now, almost never do we leave it there. Instead, we write it this way. So W is C, and I usually use a capital C with little serifs, E to the KT. And then at this stage, students go, hold the boat, what just happened? How come the little c went away from the top and came to the front, and it turned into this capital C with these little serifs on it? What happened? And let me just remind you again, this goes back to Algebra 2, for example. If I had 10 squared times 10 cubed, you would write that as 10 to the 5th, right? Base is the same, you add the exponents. Okay, so if I had 10 to the A times 10 to the B, you would write 10 to the A plus B, yeah? Bases are the same, you add the exponents. Okay, so what we have here is we have E to the KT plus C. So one thing we can do, you almost never write this step, but let me do it just to try to keep you happy. This is E to the KT times E to the C, right? Bases are the same, yeah, the exponents. But E is a constant, it's about 2.7, and C is a constant, we don't know what it is. But a constant raised to a constant power is constant. It's still constant, right? So you know what I'm going to call it? I'll call it capital C, right? And instead of sticking it on the back side, I'll stick it in there. So W is C, E to the KT. Okay, so that takes care of that explanation. Now, this is called the general solution. Right? You need to have some of the terminology. The general solution. We know it's exponential in form, it's exponential growth, right? Exponential growth, assuming the constant here is positive, and this is growing exponentially. But we don't know what C and K are yet. So we have to figure out what C and K are. We're going to use the data points. Here was one of the data points, W of 0 was 2. Let's use that data point first. We'll put 0 in for T here, right? And the functional value, the weight, was 2, so we put that in over here. So we'll get 2 E to the K times 0. But K times 0 is 0. E to the 0 is 1. C times 1 is C, which is equal to 2. Yeah? Okay. So C is equal to 2. Now, once you have that, you go back to your general solution and you write it again, except you replace the C with the 2. So now we have W is equal to 2 E to the KT. This is still general. We don't know what K is yet, so now we have to use our second data point. So W of 2 was 3.5. Remember, 2 months in, our puppy was 3.5 pounds. You never held a 2-month-old puppy in your arms, have you? You're supposed to go, oh. I mean, this is sort of yicky. You ever hold a brand new puppy? They're all wet. They come out before mommy licks them. Before mommy licks them clean, you know? Okay, let's put that information in and try to figure out what K is. So the W is 3.5, that was the weight. K we don't know, but T was 2, that was 2 months, right? So we have K2. Should have been 9 months, because then we'd have K9. Yeah, but that's a mountain, right? So we normally don't write K2. It would be better to write 2K. 2K. Okay, so that's an equation. The only unknown is K. We're trying to figure out what K is. Let's solve that for K. Now again, this goes back to our Rosetta Stone. Remember this idea here. Now we have an exponential form, and we're trying to solve it. So, I mean, if you look at the exponential form that we've got, this is, well, I guess the first thing we should probably do is get rid of that darn 2. So let's do that. We have 0.5 divided by 2 is e. Yeah? Okay, so here's my Rosetta Stone. E to the 2K is 3.5 divided by 2. That's the exponential form. And now you want to turn it into log form. So this is log base E, right? Do I write log base E because I'm in calculus class? No. It's a natural log. Okay. It's a natural log of what? Somebody said it. Natural log of 3.5 over 2. Right, 3.5 over 2 is equal to 2K. Right? Notice, look, the exponent is the logarithm. These are the same. So the exponent is the logarithm. Those are the same. That's why you use that pattern to sort of help make sure you know how to do your algebra. Frankly, the only calculus in this entire problem is doing the integration. This is the calculus step from year to year. Everything after that is algebra. Algebra, algebra, algebra. Okay, so what have we got? We've got, if I can find it, we got the natural log of 3.5 over 2 is 2K. So K is 1/2 the natural log of 3.5 over 2. And yeah, I could bring that up to the 1/2 power. I could call it the square root. I'm going to leave it like this. Now, what are we supposed to do with that K? We're supposed to take that, plug it back in. Oops, if I can do this without, come on, baby. This stage right here, and plug K. K was equal to 1/2 the natural log 3.5 divided by 2. We're going to take that and plug it right there. Once we do that, we have not a general solution anymore. We have what's called the specific or the particular. Sometimes you'll see that. The particular solution. Okay, and to do that, you have to replace the K with what it's equal to. Okay, so the specific solution for our problem, W is equal to 2 E to the 1/2 natural log 3.5 over 2 times T, right? That is the particular solution. Now, remember, in this problem, we wrote down the answer in 10 seconds, right? Because there's a shortcut for this type of problem. We know that given this differential equation with those two data points, you could immediately write down W is equal to 2 times 3.5 over 2 to the T over 2 power, and you're done. You have the answer. You don't have to do anything else. That's why this is a multiple choice problem. You should be able to get the answer for this problem in a minute. Right, take your calculator, plug 3 in there, and then you choose this. I think that was the answer. we're going through it the long way because there are some problems that do not have shortcuts. This is the answer we have right now. You know, one of the things you should do just to convince yourself is we haven't made anything up. This is the same as 2 times 3.5 over 2 to the t over 2 power. And a lot of times students go, I sort of followed this. It was a real pain in the neck to do, but I got where you got all the k's and the c's. Where did that thing come from? So a little bit more explanation. And if you saw the video, I mean, I trudged through the snow both ways uphill to school to record that video for you. I wrecked my car, you know, got it out of alignment, came up here, I was all wet and crying, and I did that video for you, and you should watch it. You really should, yeah. What do you do here? Well, one of the things you can do is to take this 1/2 and hook it up with the t. So I have t over 2. Like that? Yeah? Same thing. And the next thing you can do, you did this back in Algebra 1. If you had 10 squared cubed, what was that? 10 to the 6th, right? And the rule was if you have an exponential expression raised to an exponent, you multiply these together. Okay. So if we had 10 raised to the a raised to the b, I could write that as 10 to the ab, right? ab. Because you multiply the exponent. Okay, so if I had, suppose I had k to the pq power, I could write it 2 ways. I could write it as k to the p raised to the q power, right, like that. Or I could write it as k to the q raised to p power. Both of those would be right. Okay. So let's see what we've got. We've got e raised to this number, that's just a constant, the natural log of 3.5 over 2, times this expression. Okay, so what I'm going to do is I'm going to write it this way. W is 2e to the natural log of 3.5 over 2, and then raise that whole kit and caboodle to the t over 2 power. Okay? Why do I want to do that? Well, one of the things that you should take away from any algebra class or pre-calculus class is e to the natural log of stuff is stuff. The exponential and the log functions are inverses. They can do each other. So when I see e to the natural log of 3.5 over 2, I can just replace this bracketed expression with 3.5 over 2. And lo and behold, there we are. Okay, so the shortcut gets you there very quickly. Well, it depends what you're supposed to do. If it says find the function w, right? Now, if it's an exponential growth or decay problem, just write the answer down. You don't have to go through any of this stuff. 7.3 are probably, let me give you the first problem in 7.3. It's the example. You can look in your text if you want. It says dy over dt is k square roots of y, like that. K square roots of y, where now the rate of change is not proportional to the amount. It's proportional to the square root of the amount. This is not exponential. For exponential growth and decay, the rate of change needs to be proportional to the amount. That's exponential. But as soon as I put something else in there, that's not exponential. So there is no shortcut. So now you've got to do it the long way. Okay, so now we're not going to have time to finish this, but you can certainly look at this tonight. Tonight I want you to look at example 1, 7.3. This is called the leakage problem, the tin can leakage problem. It's on page 324, right? Page 324. So you do this leakage problem, and then look at example 2. That's a tin leakage problem. On page 325, 326, 327. Yes, it's 2.5 pages. It's a really, really long example. But let's go ahead and start. What's the first step? Separate the variables. You have to do that. You have to separate the variables. Okay, and the way we do that, all the y's go on one side, dy divided by the square root of y, and all the t's go on the other side, k dt. Now, if you want, you could bring the k down here. That would be okay. This is still separating the variables. Generally speaking, the only thing you want to bring over to the y side is the things that you have to bring over. You don't have to bring the k, so it's actually easier to leave it like this. Okay? What's the second step? Integrate. Okay, so now we have to integrate both sides. That doesn't mean just throw a squiggle in there. That's the indication you're supposed to integrate, but yes, you are supposed to integrate. Now, the right side is the same as the puppy problem. That's kt plus a constant. The left side is not logs. There's no logs there. It's a power rule problem. So let's see what we've got here. We have got the integral of y to the minus 1/2 dy, right? The square root is the half power. It's in the denominator, so that's minus 1/2 power. That's what the left side is. Now, to integrate that, you use the power rule. So add 1 to the exponent. That gives me to the what power? 1/2. Negative 1/2 plus 1 is positive 1/2 divided by or multiplied by 2, right? The power rule, add 1 to the exponent divided by the new exponent. Okay, kt plus. Yeah. Okay, so what's the next step? We integrated. Next step is solve for y. Okay, so we've got to get the y by itself. This one isn't terribly hard. I divide through by 2. So y to the 1/2 is kt plus c over 2. Right? And then how do I get the y by itself? This is y to the 1/2. Come on, algebra. Square both sides.
There will be a softball meeting at 3 p.m. in the forum. There will also begin volunteering at Betty and Williams and Our Lady of Perpetual Help next week. Please stand.
Okay.
In the name of the Father, and of the Son, and of the Holy Spirit.
Amen.
Hail Mary,
Full of grace, the Lord is with you. Blessed art thou amongst women, and blessed is the fruit of thy womb, Jesus. Holy Mary, Mother of God, pray for us now and at the hour of death. Amen.
in the name of the Father, and of the Son, and of the Holy Spirit. Amen.
Okie dokie. Manana. Let me turn this darn video off.